We were trying to compute the electric field at some special points. So in this video, I'm going to compute the electric field at this point in here. Basically, this point is on a plane, on a two-dimensional plane, where this plane is passing through the point dipole in here, and it is perpendicular to the dipole moment vector, right? So we just consider a point which is at a distance r from that. So let's go to the problem. So basically we have a point dipole in here, and I have a point in here. What's the electric field produced by the dipole at that point? So to solve this, I need to model this dipole, point dipole, as two point charges which are separated by some distance. This is how we can do it. Again, this is an exaggeration. The charges minus q and plus q are point charges which are basically separated by a distance d, and the dipole moment in that case is equal to q times d. At the end, I'm going to assume that this the distance between the point charges in the dipole is much smaller than this distance, and so as a result, at some point I'll make use of this approximation, but I'm going to do it only at the very end. So let's draw these. I think I'm going to draw two straight lines in here, so let me get a help like that. So it is this one, that line connecting the positive charge to the point in question, and this is the line that connects the negative charge to the point in question. So let me quickly write this thing down. So the distance, the length of these lines is basically r squared plus d squared over 4, both of them. So that's the distance of the point charges to that point. So in any case, so that means the electric field produced by these charges will be along this direction. I'm going to call this as E plus, the electric field produced by the positive charge, and this direction. They are equal because the charges have the same magnitude. These two electric fields have equal magnitude because the charges have the equal magnitude and the distances are the same, right? So what we need to do, therefore, to compute the vector sum of these two is to do a vector addition. So we know how to do the vector addition, so you just need to join these vectors tip to toe. So for example, E minus would be a vector like that, or you can take this as the E plus. In any case, this is the vector that we would like to compute. So that's the electric field. Okay, again, we have a vector addition in here. The electric field that we would like to compute is E plus E minus. But I can carry out this vector addition in the form of the components. Let me do it like that. So I can carry out it in components. So since the vectors are in general in two dimensions, I need to do this component addition in at least two different directions. In any case, let's choose our axes. So I'm going to choose the x-axis like that and the y-axis like this. So in any case, along the y direction, so let's just call this angle as theta, and that angle is also theta, and that's 2, right? All of these angles are equal to theta. So let's see, I'll start with the y component. E plus y has a negative y component, so that's basically the magnitude of the electric field. Let me call this as E plus multiplied with cosine theta, and this has a positive y component. So let me do it like this. So that's equal to cosine theta. In any case, in this case, it appears that the y component is equal to 0. So that's basically apparent from the picture. Along the x direction, however, both of these vectors have the same x component. Again, this is negative sine theta, and then both of them are again minus E plus sine theta. And so therefore the x component is 2 times E plus times sine theta. I just need to compute this. I just observed that sine theta is equal to d over 2 divided by square root of r squared plus d squared over 4. So let's do this calculation. So Ex is minus 2. E plus is basically the magnitude of the electric field produced by one of the charges. So that's Q divided by r squared plus d squared over 4. Alright. And then I need to multiply this with sine theta. So this is d over 2 divided by the square root of r squared plus d squared over 4. So that's the exact expression. But let's continue with the exact expression. So the first thing that I notice in here is that I still have the q times d multiplication in the numerator. So I just replace this with the dipole moment. So Ex is minus, this cancels with that, minus 1 over 4 pi epsilon 0. The dipole moment, that's basically the x component of the dipole moment. In any case, divided by r squared plus d squared over 4 to the power 3 over 2. Alright. So at this stage then, since I have obtained the dipole moment in here, so d somehow appeared in the calculation of this quantity. Now I can neglect all of the d's when they are compared to the r's. So they are actually very small, so therefore I just neglect these. So that means Ex is minus 1 over 4 pi epsilon 0 p divided by r cube. Alright, I can also write it in vector form as well. So all I need to do is to multiply this with the I unit vector, and this will be basically the electric field, and this P times I will be the electric dipole moment. So let's go back to the original problem. So in any case, we knew that at the beginning that the electric field will turn out to be opposite to the along this direction. Basically, this is the direction of the electric field, which is opposite to the dipole moment vector, and that's why we have a negative sign in here. So let me write it down like that. So that's minus 1 over 4 pi epsilon p divided by r cube. All right, that's the solution to that problem.